Well, good morning, everyone. Welcome to this EasyPower presentation. Today's subject is an introduction to dynamic stability, and we're going to be focusing on utilizing the script editor to perform more complex testing or analysis. The advantage is to be able to supply a system stimulus which will give us the ability to determine system response before we do a trial and error or risk damaging complex equipment. We'll begin with an overview of about 10,000 feet level with some discussion about what the tool can do for you, places where dynamic stability is the only tool that can provide a visual presentation of the system with key configurations, just lightly touch on the theory, and then get into some very specific examples which you can't really deal with or may not be able to capture the data with a snapshot analytical type of tool. And if this touches on any areas that you have an interest in and would like more information, I'd strongly suggest that you consider attending the EasyPower Dynamic Regional Training, which I'll have details on later in the presentation. So there are several nice features the dynamic stability module that makes life easier for an engineer. And as I say, I'm not going to spend much time on theory, but I do have some slides that I want to overview the basics and then convey some of the complications involved with dynamic stability. So as always, if you would mind participating in a couple of brief poll questions, we'd appreciate some feedback. First of all, how often do you encounter situations that you think dynamic stability may be helpful to you? And again, we get the sense that there are more potential need for this type of analysis, and there is some reluctance in engineers' ability to use it or to implement it because they don't have the tools at their disposal. So here's kind of how the audience is shaping up, and appreciate the feedback. And then finally, based upon at least the minor description or the minimal description we've offered, kind of where are you coming from with respect to your attendance this morning? Are you actually have the tools and you don't use it much, or are you just curious and you'd like to see how this type of analysis takes place? Again, appreciate people closing that feedback loop with us. So again, welcome to all, and let's get into our discussion. So dynamic stability has actually been around for decades, and the consequence of that is the methodology that's used is actually well proven and follows the general simulation methodology that we see in many other tools. Dynamic stability assumes that we're most interested in a time response that's really no smaller than a half a cycle. So this excludes a sub-cycle fast transient analysis, and the focus of the time response that we're looking at right now is primarily machines and control systems and electromechanical responses. The term transient is usually reserved for fast sub-cycle effects, but even that area, as we explore dynamic stability, is encroached upon some of our discussion because we describe things like impact motor starting or transient motor starting as something that we can do with this tool, and it unfortunately blurs that line. But the bottom line is what we're trying to study is the interaction of electromechanical devices, motors, generators, and we're primarily interested in the RMS response of about every half cycle. So what can EasyPower do for us in terms of dynamic stability? We can analyze the many forms of motor starting and their impact or its impact on the system, and conversely what the system's impact and feedback or reaction to that motor's activity in the network. We can look at sequential starting, in other words, one after another, and potentially uncover any negative results that could surface, especially ones that we're not able to identify as we're doing snapshot power system analysis or PowerFlow analysis. For instance, a cogeneration station, which happens to be fed by a utility and a cogenerator, what happens when the utility drops out? How long does it take the system to pick up the load, and is it fast enough to prevent outages of critical equipment? Can we recommend, say, a load shedding scheme that will keep critical system loads up and running until the cogen recovers and carries the rest of the system by itself? We can simulate isolated system behavior with frequency depressions or sags. We can show protective device tripping on faults and contactor dropout on voltage events. Likewise, we can evaluate fast bus transfers of motors to reveal transient shaft torques. Very difficult to identify that with a load flow analysis that doesn't include some sort of a time step. Impact loading on backup generators, whether or not they can recover from the step function in the load being thrown on as a result of a fault. We can reveal dynamic instability in a system with multiple generators, where one generator is trying to pick up a load that's for some reason cast off by another. Do we get into a critical cycle where one is trying to pick up and shed at the same time, and the overshoot causes reverberation across the network? We can also show fault critical clearing time for cogenerators connected and supplying power for the grid, and at the same time simulate the most detailed form of arc flash analysis. We'll touch on that briefly at the tail end. Cogenerator clearing time, when the fault has been cleared, does it overshoot the need to pick up the load, and does it go so far that it can't recover from that instability? We can confirm proper excitation systems, tuning of both the voltage control, the governor system, and match the physical system or system test in the field with the way the simulation has been modeled, and verify that we have better matching or more accurate matching between our system simulation and the actual system that we're trying to model. So actually test data can be staged and compared with what the simulator produces. We can also perform data tuning simulations and match those test results with the generator's model, the exciter, and the governor parameters. We can evaluate plant internal voltage depression conditions due, so like voltage sags, even utility side system faults, brownout spikes. Interestingly enough, something that doesn't show up in short circuit study and is very difficult to extract from just looking at time current characteristic curves is the potential fuse fatigue and relay over travel whenever we have race conditions during a fault, either an arcing fault or a bolted fault. We can also show protective device race conditions. We can use dynamic stability entry as a PowerFlow solution to supply higher accuracy PowerFlow that includes motor machine equations and its determination of the motor VARs and the response to changes in loads in the system. We can simulate governor mode changes from droop to isochronous control, and even when that's an automated function within the generator. Likewise, discover backup generator response to a transfer switch activity, and especially when it's automated and in response to a fault or a change in load. And the list goes on. So it's really valuable, and what we're trying to do, rather than get into all the details of the simulation itself, is to hopefully open your eyes and show you what the capability of the tools are, and leave it to you to verify the application within your particular requirements. So let's kind of start from there. How does it work? First of all, as I mentioned before, there's three main parts to the system, and it uses a proven modeling knowledge of machines and control systems behavior to simulate a real-time electrical system response. Now a big part of this is the network, which is the cables, the transmission lines, the transformers, the busways, and etc., which link the models together. So each model, each machine, each generator, each element has a model that's been developed, and they are interconnected through the network, which is, in essence, the database that we've created as we do a one-line diagram or constructed a short-circuit study for arc flash. And so it links together the models, which are the common three-phase balance domain. So just note, EasyPower dynamic stability uses a positive sequence, balanced, three-phase simulation. We're actually not working on or not utilizing an unbalanced system at this time, at least not yet. And then finally, EasyPower dynamic stability uses a method of numerical integration to progress systematically through time to give us this real-time simulation. So the models are built and function modularly, and they respond to clearly defined input and output parameters. Consequently, they react to the network via their terminal conditions and each other. For instance, generators, excitation systems, governors, motors, motor loads all connect to the system, and based upon their terminal conditions provide a change of state that then is connected back to the other models through the network. And then these models react to the network conditions, which would include the protective devices, switches, ATSs, contactors, and the like, which may respond to these changes or new states which the system will find itself. So the model types that we have and we'll see in the system are generators, generator excitation systems and governor systems, motors, several different types of motors, motor loads, all the power protector and protective devices which actually we have in the database for the most part already. And then we're adding the models of the transfer switches, over voltage, under voltage, over current, over frequency, and under frequency relay responses, which don't necessarily show up in the short circuit studies. So here's how it all's connected together. For instance, a generator system model would have the generator here, which is a rotating machine, and it's linked to the governor system. The governor system consists of both a governor simulator and a prime mover simulator or model. The excitation system model over here includes the automated voltage response, a regulator, an amplifier, an exciter, and an alternator, all enclosed or encapsulated in the excitation system model. And then some systems, we're not going to talk about it today, but some systems include power system stabilizers. So if you'll notice, there's specific linkage between each portions of this model that include the ability to provide the mechanical power to the generator model, and as a result, what the change in speed will result or come back from the rotating machine simulator. Likewise, the field current that goes to the excitation module will provide a response in field voltage, and this is connected to the network through a Thevenin equivalent impedance and an impact signal of Thevenin voltage, which can then show the result or the change due to the model's response. So likewise, the motor system model is similar, except it doesn't have the regulation included or the field controls included as we do in a generator. It does have an induction motor model and then responds to changes in speed and torque, mechanical torque from its rotating load. And again, this model will connect to the network through a Thevenin impedance and a Thevenin voltage that will be calculated at each time step. So the machine model features, all the machine models include frequency effects, voltage effects, saturation, and inertia effects. And we'll see that as we get into these examples. And most of these can be modified or affected even as we're stepping through the calculations by the functions in the script. So now we talk about the foundation being the network itself. The network is the connection between all these various models in our system. And as I say, it's been constructed for the most part as we do a one-line diagram in EasyPower. And so now we're utilizing that data that was collected, that one-line diagram that was originally constructed. And the initial step is to solve that network in a PowerFlow environment. And that solution, or that PowerFlow result, is used to determine all initial conditions when we enter dynamic stability. It's necessary to make sure that we're in a stable state so that any migration or changes in elements or parameters is as a result of the stimulus that we want to provide, not some imbalance that was introduced because we didn't have a stable PowerFlow. So the network is used for all inputs, and as the protective devices reside in the network, the input then from the models will be connected to or relayed to the protective devices through the network, and then they will simulate their action in real time. And as you'd expect, it's also used for scripted and automatic switching, which we will get into briefly. So now many elements inside the network, as well as all the model inputs that we're going to be setting up, have stability tabs. And so what that means is there's some need to augment what the database was, the network was that we first described, because what we're going to be generating as the development of these models is referred to as a full flux model for rotating magnetic fields. We utilize a numerical integration methodology that has been well proven, and it's a methodology that's been utilized for decades. We put our own spin or approach on it. We regarded or referred to as the modified Euler method. But we've defined a state that can be calculated as a condition of the model itself and is responsive to time. So therefore, if we define a current state or the present condition of that component, the future state of that component will be the current state plus the change, the delta state, times the time element or time step that we're encountering. So this brings us to the dynamic stability quandary. Why do engineers stay away from dynamic stability? And as we're kind of talking about this, you'll see we have a lot of data, and the initial short circuit analysis requires a fair amount of data to start with. And so, in my opinion, the primary reason that engineers shy away from dynamic stability is the fact that there is a need for far more detail in terms of data for generators, excitation systems, governor systems, motors, and more. For instance, if we just look at what's required to go into a model for a generator, we'll see that, and we've had exposure to these over time, but it's not something we use on a day-to-day basis, involving most of the sub-transient reactance parameters, and that's only the half of it. Then we get into the time constants for each of these parameters, and there's not always equal correlation between what manufacturers supply and in some cases what a simulation tool requires for input. So that's just the generators. If we look at the other elements in the system, including the governor systems, induction motors, synchronous motors, motor loads, and all the other elements we've been talking about, it does compound this problem about having or requiring data. So what we've proposed, or what we've done in terms of supporting dynamic stability, is we provide a library that has a significant amount of typical data as we pick up each one of these elements, and we're going to get into that in a fair amount here shortly. The value of the typical data is that at least you have a starting point and you can make a first order approximation of what the response will be, and as these are developed and refined, you can improve those parameters and the data that's been used as a typical starting point to improve or sanitize the data that you ultimately use for your simulation. So among other things, the data we already have is that protective device characteristics and TCCs, which are utilized for coordination and arc flash analysis. In each of the elements that we're describing, for instance, a motor data dialog box, there will be a stability tab, and by invoking motor modeling, the data for models for that motor can be entered, and we're going to show how to access the typical data library as we get into this. Likewise for generators. The stability tab gives us the ability to both enable the model, but then bring in from the library typical data. As part of our demonstration, we're going to show what the one-line diagram will illustrate, along with the real-time parameter changes and plots that can be customized based upon what we're trying to learn. And as I indicated, the place we start is the stabilized PowerFlow solution. Functions built into the tool are both double-click and then the scripts, and how to incorporate those is where we're going to be spending most of our time. And before we leave the subject, we will explore a fair amount of data that can be derived from the log, the message log, because there's a lot of things going on that we won't necessarily catch in a, as I mentioned, a snapshot environment. So let's jump out of this and get into the example that we pulled together. Now this is an example that's actually in the sample library, sample installation of when you install EasyPower tools. And we started with Dynamic Stability 2 example, which is essentially a cogeneration station where this is a utility. Here's my cogenerator. Here's my my emergency standby generator, and then several loads that are included in this station. And the first thing we're going to do as we enter the stability focus is verify that we have a stable power solution or PowerFlow solution. And so that's what we see here. As we kind of go around the system, we can see the real PowerFlow versus the imaginary PowerFlow or reactive PowerFlow. And if we go up and look at our cogeneration station, one of the things we can tell by looking at this is it already has the data in it for simulation. The elements for the model include the rotating machine, which is indicated by this rotor symbol, the AVR or excitation system, which is included by the winding or denoted by the winding, and then the regulation or feedback for the power control is indicated by this little bow tie looking system over here for our amplifier. Now let's just conduct a load step test. By double clicking on the excitation, what we see is an open loop step test that shows the terminal voltage coming from that cogen, its field voltage, and then what the VAR generation per unit is as a function of that input. Let's load step test the control system. We see the same type of response to the step load and the recovery. And you can see this over spikes, then comes back to a steady state condition. If we go down to our other system generator, we can perform the same. So all I'm doing is double clicking on the icon in that particular element. Again, the excitation system for emergency standby, this is much snappier and has less overshoot and a quicker response. And likewise, the response to the load step test on the regulator. Okay, so that's again built into the double click function of the tool itself. So let's go back now and add a motor. So we're going to go back from the stability focus to the database editor. And what we see here is a series of several voltage buses, and I'm going to come back from our ribbon input. We're going to add a motor on this 480 volt bus, and we're going to add a low voltage power circuit breaker. I'm going to copy exactly what we've seen here on the other loads to have the same breaker. And in this motor, now granted these are somewhat hypothetical because we're using large motors for our 480 volt bus, but let's say we want to look at a 500 horsepower motor. First of all, when we go into short circuit and calculate it, we can see that it's taking by default all the standard power factor and efficiency data that we have on the ANSI standard. As we enable the motor model, though, we have the ability to bring in library data. In this case, Rockwell has a large list of all the different motors in the library. And before I jump into that, let me show you essentially what the libraries have. So in the library, there's a specific nomenclature or a scheme for labeling each of the motors. So there's a type of motor, the horsepower, the synchronous RPM, and then what specific design code that is related to that model. So as we come back here and look at this, we'll see that we're going to look for, under the Rockwell, a 200, the largest one we have is a 200 horsepower, 1200 RPM motor. We're going to bring that in as our typical data. And in this case, we're going to say, yes, we want to override it because we want to try to work from this model that we have some amount of confidence in. And so now as we import that, by default, it gives us this speed squared for both starting and running load. And as that varies from 0 to 1, we'll end up with the same result, but we'll have a squared curve for the performance. Now, if we have a specific data sheet or the torque speed curve, we can actually bring that into the tool and digitize it from whatever the manufacturer's data sheet has given us. And this can be pulled in as a source of data, actually more accurate for our specific application. But in this case, we're going to start with our typical data model. Now, as we go back into dynamic stability, let's kind of widen up our screen a little bit. So the first thing we want to do is test what the effect of starting this motor is on the system. And just by looking at it, you can see the motor is already included as online and as part of the PowerFlow calculations that are being illustrated. So the first thing we want to do is to open and resolve. And as we do that, you can see the entire system has resolved the PowerFlow solution. That's the initialization point. Now another double-click function that's built into the tool, and the tool is smart enough to know that we're going to be operating a breaker in line with the motor, is by double-clicking on it. And now this shows us the simulated response over time of applying full voltage to this motor. We see there was a voltage sag, and then as it comes up to speed, the motor voltage, terminal voltage goes up to normal operations. So we have the terminal voltage, the current, per unit current, and it's high current as the motor comes up to speed and then drops down to quiescence. The motor speed is being shown, and then here's our electrical torque. Now you can see here that this takes approximately, we go for 1 second at stable operation, and then we start the motor, and the motor looks like it's up to speed right at about 2 seconds, which means we have a 1 second start time. Now, directly proportional to start is the function or the parameter, in this case of the motor, the inertia. So as we go back to our stability tab, we find inertia, which is here the H factor, kilowatt seconds per kVA. We see it's at 0.4. So if we double this, we would expect to have some linear response or result impact on the starting time. So let's change that, go back to stability, start the motor, and sure enough, we see now starting at 1 second, the motor ramp takes, we're coming out here about 3 seconds, so it takes twice as long by just changing the inertia, and consequently that's one way of tuning what our actual system is compared to the typical data we're starting with. So in just that long, we've actually added a motor to the system. We've created a what's effectively a system response to a motor of this size and parameters that can be adjusted, and we can make some assessment about whether or not our system is capable of handling this type of addition. So now, what happens if we want to change? Well, we can change any of the motor parameters. In this case, we saw the inertia variable changed, and you'll see later that we can actually change this during the cycle, change any of the parameters during the cycle with the script control. So let's try a more complex task. And as I'm looking at this, you'll notice that we show here that during this simulation, at least this one contactor went from open to closed, which is what's the reason for it being highlighted. So we're going to reset this simulation and go back to our initial starting case. All right, so the next thing we want to do, if we look at this loading here, is that we have a couple buses at 480 and a large another bus at 4160. So right now we have none of these motors online. Let's see how the system responds to the sequential starting of each of these motors. We're going to do that with a script that's called sequence M4, 5, and 6. The way we've created that is with the script editor, and as we go in and look at that particular script, the tool has only a finite number of commands that it will accept, and it's not a matter of typing them in, it's a matter of selecting them from the list of commands. So what we're going to do first is run for 1 second to verify steady state. Then we're going to close each breaker in turn, run for 2 seconds and close the next one, and then run for 3 seconds at the end of the exercise. So now if we've made those selections, let's go ahead and pick the script, run the script, and what we see here, if we look at and the first thing that you need to notice is that we're actually plotting a series of customized plots, or displaying a series of customized plots that we can control, and we'll show those or how to set that up in just a second. All right, so what we're doing here is comparing the voltage, the MCC3, which is the third plot here, or the third curve. This is actually the motors as they're being brought online into the system. And what we're plotting here is the effect or the voltage response on switchgear 13.8, which is up here, and the source or the control point for the utility, connection point for the utility, at MCC2. And so we're seeing, if we kind of look at the details here, a significant amount of impact as we're bringing each one of those motors online. So if we look at this, what else are we can also plot the, in this case, each of the motors' specific voltage and current spikes. Let's plot, we're looking at the cogeneration response to these motors coming online. We didn't point out earlier, but I'll get back to it in a second. The system initially starts out at a neutral position as far as the information, the data power coming from the utility. So we're pretty much at a null point between the power the utility's drawn, and we come back here and we look at the cogeneration connection point, it's generating about 6 megawatts. So as we run this simulation, it's responding in kind, and as we're looking at the cogeneration voltage, terminal voltage, you'll see that it droops when we see the load come on, the motor come online, and then it actually overshoots the voltage, system voltage, before it's brought back down, and again being driven by the field, the cogen field control. You can see it's overshoots, comes back under the quiescent point, responds again to the next motor coming online, and again it's what you'd expect or what you would hope to find. But one of the transactions that we didn't expect is the fact that we're actually getting voltage above the normal control level, in spite of the fact, and it affects even the other motors on subsequent or sister buses. So this first one is a utility bus. The second one's MCC2, which is another 480 volt bus, and then even the 4000 volt bus. Let's look back down here. Okay, so the next question is, well, what happens, or how would this look if the utility wasn't involved in providing the buffer for some of this compensation? So we come up with another script now. Instead of just running the sequence of motors, the first thing we want to do is drop the utility. So let's look at that. And so now you see we start with the same 1 second stability run, then we open the high voltage breaker, the utility, run that for 3 seconds so that things stabilize out from that initial transition, and then again close each of the breakers and run for time. So let's see how this looks. Now things get a little bit more interesting. So again, we're looking here at comparing each of the buses. Now we've lost our utility bus, so it's not going to be in the picture. And what we see are the sister responses on the 13.8 switchgear. Again, the third plot, or the response to the motors coming online. And even the impact on MCC4, which is the higher voltage bus. And in each case, we see there is exposure to higher than normal or higher than expected. Looks like we're getting up to about 107% of the nominal voltage. And this is a very typical response from an isolated system that's working off of a generator when you have a large motor starting in the line, and how it impacts the rest of the system. So this was an argument, frankly, to go out and evaluate motor control systems that don't go full voltage across the line. So the next thing we want to look at, next example we have set up, is how does the ATS respond to a system fault? So what we've set up for is the ATS to respond to a loss of power and switching over to the standby backup generator, and there's really no motors involved. It's basically a linear load, but again, it's a function of the double click feature. We don't even need a script to do this. So we're going to fault the bus up here, expect it to be cleared probably by this fuse. And so what we see is the fuse has cleared. We've lost voltage on this bus, and we show in the auto plot effectively on this bus that we're looking at a loss of voltage in the current spike that would be the fault. But if we plot the response on the ATS, we see now it's transferred over to the other side, and what we're looking at here is the terminal voltage on the standby generator, again where it comes online It accepts the switch over of the voltage to the standby condition. The current pickup, the speed pickup, or impact on the speed. The field as the load starts to stabilize, and it seems to recover, transferring over that load within a fairly short period of time. So that's essentially what we're showing here between plots 3 and 4. Plots 3 being the cogen terminal generation, terminal voltage during the fault, and then we delay subsequent changes there because we have the standby generator coming up after it gets up to speed. Now, part of the, as I mentioned before, part of the advantage of having the tools is being able to see what's going on behind the scenes as each one of these elements take place. And that's the function of the message log. So what we're showing here is from the time we had a bus fault that the contactors picked up. We'll see if we come back over here during this transition. The contactors picked up but didn't fault out. The relays picked up on overcurrent. The ATS picked up on under voltage, and you can see where the relays traveled back after being reset from the fault clearing. And in some cases, we can see that we may be reaching a point that may impact future operations of that particular device. So a case in point is if we fault bus, let's go back and reset this. And now let's look at what happens if we fault bus MCC4. So let's fault this bus right up here. All right, so here's the plots right now for the cogen and what happens to the load as a result of that particular fault and how it recovers. Actually, the field collapses and then goes through recovery to bring the rest of the loads online. And what we see is the relay cleared the fault, and we don't really see anything as far as the final state as what may have happened to the fuse. However, if we go to the message log and get into this, we see that the fuse that I'm looking for did I fault the wrong bus? Let's try that again. So what happens if the bus faults here? So again, the relay cleared the fault. We still didn't have any fuses to clear, but we can see here we have a fuse that reset at 74% of its trip curve, which means this fuse potentially is fatigued and we may not be able to depend upon it operating normally or per the spec if it's dependent upon to clear a fault in the future. Again, not something that necessarily shows up on a TC curve. So I find that pretty interesting. It's something that you wouldn't think to look for. Okay, so this next one is pretty cool. The next one's a voltage sag, and the question is, how will our system respond to a, let's kind of go out to the whole one-line diagram. One of the techniques in modeling is if we want to simulate a sag on the utility line is to model a very long run of a transmission line, put a fault on it that will generate a predetermined amount of current. For instance, if we fault this in short circuit, we can see how much current it generates, and it will be cleared by this relay. But the question is, what type of an effect does that voltage sag have on our switchgear and our internal system, and consequently the value of dynamic stability. So we're going to take this, again, we're going to apply the fault, which will give us a, let's start with a 3-cycle sag, and look at, so this is again our fault on the utility bus, and what we're showing here is the effect on each of the buses. There was a sag, and it was approximately 3 cycles. And how did it affect the rest of our system? There were some motor implications, specifically, here's my cogen current responded to pick up the load. There was a spike on M1, and if we kind of look through our results, we can see that we lost a couple motor contactors in the simulation, but it seemed to survive pretty well other than the loss of these 2 motors. So let's try a 6-cycle sag by faulting this other bus. And again, now you can see the fault lasts much longer, and if we look at our end results, we lost those same 2, and we pretty much lost all of our loads in the on the motor side. So again, we're examining how the system responds to sags, which is not that relevant to short circuit, strictly a short circuit analysis. All right, so one more thing I want to do as we get into writing a script. See what other scripts I had. We did our sequence. What I want to do is take this motor that we added a while ago, which was M3, and when I go into the script editor, I'm going to go back to my database editor, open up this particular motor characterization data dialog box, and as I look at my stability tab, I want to modify some of these parameters, and the way I do that is I right-click, export it to Excel, and let's open it up. And so now what I have access to are each of these parameters in my script edit mode. And so I'm going to take out this first row, just delete. So now the first parameter is rated horsepower, the second parameter efficiency, and so on. And I'm going to assume, I'm going to ask myself, how can I simulate a condition of the motor starting when I have, let's say, a load that changes, let's say a clutch that changes the torque on the load, provided the feedback from the load to the motor. And so I'm going to effectively simulate that by a change of inertia. And in this case, we're going to start at 0.8 and see what happens when I change that after the motor gets partway up to speed. How does that affect the rest of my system? So to do that, I'm going to write a script. So let's go back into dynamic stability. We're going to be working on BL3. Let's go ahead and close and resolve it. Now we're going to write a new script. Let's call this load change. Now, you may have a better presentation of what this, a better way to simulate this, but this is just a for instance on what the tool can do. So the first thing we want to do is run for a specific time, and that's 1 second. Next, we want to start the motor. So I guess I want to go back and open that up. So this is going to be BL3, start the close the low voltage breaker. Then we're going to run for 1 second. And then let's change that parameter in the variable. And the way we do that is pick out the command set motor parameter. We're going to set it on M3. And from looking at our spreadsheet Excel format, I can see that parameter number 23 is the inertia parameter I want to change. So it's variable number 23. And we're going to change it to something much larger, let's say 1.5. And then we'll run again for time. All right. So we need to close that. Let's go ahead and open and reclose, resolve. Take out our data view, pick out the script we just wrote. Now at the same time we're going to plot some new curves. So let's see, what we want to do is define new plots. Let's pick out condition of our motor. So we're going to look at motor speed. Let's look first at the current and M3. Let's look at the speed on M3. And then while we're at it, let's look at the torque and per unit. And we've got a couple terms here we haven't set up, so let's go ahead and finish those in so we can see what the cogen does it during the same simulation. Okay. So we have something with 6. Let's go back and do it. All right, so the motor's open. We're going to run our load change script and see what the results are as far as the motor's operation. All right, so again, we start at with one value of the inertia, and then halfway through the start cycle, or most of the way through the start cycle, we make the adjustment there. So what we see are the current that's delivered to the motor over time. It's electrical torque that's being provided, and it's a response to that change in loading. And it's not, frankly, not what I expected. So it's something of an eye-opener at the same time. We can see what the impact is on our cogeneration for having this change in load, how it's going to affect the rest of the system. And again, we just saved ourselves a fair amount of money if the experiment had turned out bad for the system. Okay, so that's, I guess, the one last thing I wanted to do was to go in and do an arc flash. So now we've shown the script. We also want to end up with doing kind of a calculated arc flash using EasyPower options. Just while I'm here, this is where we can control all the parameters of the dynamic stability. So as we were double clicking on different elements, this is what determines what's shown in what the operation is and what's shown in our auto plot here. And then when we're going to calculate arc flash, we're going to use arc flash simulation for faults. We're going to use 100% arcing current. I'm going to go ahead and apply this. And now as we go back to our system, let's come up here to our 13.8 bus and double click on it. And what we expect to see is the simulation of an arcing fault on this bus, what happens to the, in this case we're plotting the cogen response to it. You can see that the arcing current was supplied by the cogen until it started to recover. So here's the voltage, the current, the cogen speed, and the mechanical power. We plotted, here's the arc flash itself on the switchgear bus, and the significance is this is the actual current, excuse me, so the voltage on the bus and the actual current during the fault, and you can see where the different parameters, the cogen tried to keep the fault current up until the relay tripped off, and then there's the PPE, or excuse me, the incident energy that's being calculated for that time, and all of this is being shown in our log down here at the bottom. So what would happen if we go back to our options and select 85% arcing current and run the same result, fault that bus, and we see quite a bit of a different change here in terms of the lower current and how our system responded to it. So again, this is insight that we won't find on a TC curve. It's a real-time display of the arcing current if we had an arcing fault on this particular bus, and its impact or its interaction with the cogen to sustain that type of a fault. Okay, as much fun as this is, I'm getting to the point where I need to wrap this up. I appreciate everyone for joining, and by all means, we'd be more than happy to entertain more inquiries, folks that want to learn more about this. You're welcome to contact tech support. We essentially did load step tests for the generators. We've added motors. We use the library data for typical motor response. We've illustrated the double-click functions. We've changed motor parameters in the file, in the typical data file. We've used scripts to craft complex sequence of events. We've shown how to simulate an ATS conversion or convert over. We've utilized the log file to mine for other data that we didn't necessarily expect and had no other way to measure. And then we've shown how to use new scripts to change parameters as certain events are going on. So as you can see, the bottom line is dynamic stability can simulate a lot of system responses that we have no other way of looking or measuring. And in many cases, it's the only tool we have aside from actually testing the gear in place to determine certain results. So I would basically refer to it as the ideal environment for a what if, and we actually have people that utilize these tools to say, okay, if I have an existing facility, campus, air base, whatever, and I want to install a PV farm next to it or a wind turbine farm next to it, how's that going to interact with my system? That can save you a ton of money answering the question in a simulation platform before you get to the actual real world. So I'd like to invite anyone that has an interest in learning more about these tools, learning more about the use of these tools, to consider registering for the harmonics and dynamic stability class we're holding here in Portland in late October. There's a lot of other resources available by accessing tech support at EasyPower.com. Be happy to discuss with anyone the need to expand your capabilities in terms of utilizing our engineering services group to back up your need for extended capability on a project-by-project basis, and be happy to carry on that conversation with anyone else in the audience. Sorry, I see there's several questions, and I'm apologizing for not having the time to get to them right now, but certainly anyone that's entered questions, I'd be more than happy to, we will answer offline, and I appreciate everyone for attending. Have a good day, and we'll talk to you down the road.